Alrighty guys, let's go ahead and take a look at this problem right here with Mr. Melquist. It says Mr. Melquist is at a grocery store shopping for ingredients for dinner. He is pushing a shopping cart which includes his groceries. It has a mass of 56 kilograms. When he turns down the gluten-free aisle, he sees Mrs. Kaler race for the last package of gluten-free pizza crust. Mr. Melquist pushes his cart with a force of 70 newtons directed downward at an angle of 11 degrees. His cart accelerates at 0.22 meters per second squared. So he's pushing down on this cart. So here's my downward push, and it says that it's at an angle of 11 degrees. So I'm going to draw that right here. Cool. We got some questions. Before we look at those, let's finish our free body diagram. So I'm going to take this information that I just drew and draw it again down here. I know that I have force gravity acting downward on this cart. I know that he's pushing down at an angle, so I'm going to draw that as well. That would be my force applied. I have force normal pushing up. I know normal is going to be bigger than force gravity in this case because of the applied force downward, meaning that the surface needs to push up more than force gravity is pulling down in order for it to remain in equilibrium in the y direction. It also has some friction, so I'm going to go ahead and draw friction pointed to the left, because if this is my ground right here, the cart's going to move to the right, so friction is going to point to left. I'm going to separate my force applied into the x and then into the y as well. And now I can go ahead and start solving. First question says, what is Mr. Melquist's force applied in the x direction? So this one shouldn't be that bad because they give us a lot of data. It tells us that the force applied is 70 newtons. So I'm going to label that as 70. And I also have the angle as 11 degrees. So now I'm going to take this triangle and expand it outward. And I'll just draw that right here. I have x and y and my force applied. So the angle is 11 degrees. The force applied is 70. My x is right here and my y is right there. In this case, the y is the opposite side and the x is the adjacent side. So if I want to solve for x first, I'm going to go ahead and use a trig function. I have adjacent and I have hypotenuse. So I'm going to need cosine. So I have cosine of 11 degrees is equal to adjacent, which is my force applied x, divided by my hypotenuse, which is 70. Multiply the 70 over. I get 70 times cosine of 11 is equal to force applied x. After I solve for all that, I find out that the force applied in the x direction should be 68.72 newtons. And 7271 just rounding. All right, so number two. Number two says, what is Mr. Melquist's force applied in the y direction? So I need to do the same thing, except this time it's the opposite side, so I'm going to use sine. So I have sine of 11 is equal to force applied in the y direction, divided by my hypotenuse, which is 70. Multiply 70 over, I get 70 times sine of 11, and that is equal to force applied in the y direction. I do some algebra, and I find out that the force applied in the y direction should be 13.36 newtons. Next, I have to figure out what the weight of the cart is, and we know that weight is just force gravity, and force gravity is just equal to mass times gravity. It tells us in the problem that the mass of the cart is 56 kilograms, and we're assuming that he's on Earth, where gravity is 9.8. So again, just some simple algebra. Once I do that, I find out that the force gravity is 548.8 newtons. Next, I need to solve for the normal force. So to do that, I need to write a net force equation in the y direction. So I know that net force in the y is going to be equal to the forces that point in the positive direction. We're going to say positive is up, and the positive is force normal, minus the forces that point in the opposite direction. The opposite would be down, and the forces that point down are force gravity. and also force applied in the y direction because it's a downward force. All of this is equal to mass times acceleration in the y direction, but we're not accelerating in the y, so that's just 0. Therefore, this equation is really Fn minus Fg minus Fay equals 0. So to solve for Fn, I'm just going to add these two over to the other side, and I find out that Fn is equal to Fg plus Fay. After you plug your numbers in, you get Fn should be equal to 562.16 newtons. Next, we have force friction, and force friction, we're going to have to look at our equation up here just to make sure that we have the right one. Force friction is less than or equal to mu times force normal. The next question asks us for mu, so we don't know what mu is, so we can't use that equation. So we're going to have to approach this a different way. And the other way is knowing that net force in the x direction is equal to the forces that point in the positive x direction. If I look, the positive x is considered my Fax minus the forces that point in the opposite direction, and that would be force friction. This is also equal to mass times acceleration, but in the x direction. We are accelerating in the x direction. If we look, we're accelerating at a rate of 0.22 meters per second squared. So I'm going to write Fax minus force friction is equal to, again, mass times acceleration, because this is the information that I know, and then that's the one that I'm missing. Therefore, to solve for force friction, I'm going to add force friction over and subtract Max, so I get Fax minus Max is equal to force friction. Doing the math, we find out that force friction is equal to 56.22 newtons. Now that we know what force friction is, we can go ahead and solve for the coefficient of friction. So if we look up above, we can see our equation right here, and we have force friction is less than or equal to mu, which is the coefficient, times force normal. So go ahead and write that down here. Force friction is less than or equal to mu times force normal. So to solve for the coefficient, I'm going to divide force normal over to the other side. So I get mu is equal to force friction divided by force normal. Force normal, we said earlier, is 562, and force friction is 56. So if we plug both those into our equation, we find out that our mu, or coefficient of friction, should be equal to 0.1.